Student, coming back to this chapter of statistical mechanics. So in this class, I am going to explain what is the meaning of a black body and black body radiation and what is photon gas. And also I am going to derive the Planck's law of radiation based on statistical mechanics. So before going to the next part, I will see what is the this black body. So the radiation emitted by a black body is called as a black body radiation. A black body is one which absorbs all the wavelengths incident on it. So this black body is such a body, whatever may be the wavelength of the incident light falling on that will be absorbed by that body. Such a body is called as a black body. So it is having 100% absorption. So irrespective of the wavelength of the falling radiation, all the wavelengths are absorbed by the body. Such a body is called as a black body. At the same time, if the black body is heated, it radiates wavelengths of complete range. So when the black body is heated back, it radiates wavelengths of all the in the range corresponding to whole range of wavelengths. So this is the characteristic of a black body, and generally there is no ideal black body, but there are some examples which are very close to the ideal one, like for example, a lamp black. Lamp black is considered as the black body very close to the ideal one. And here we are going to explain this phenomenon with the help of this Ferri's construction. A construction is made by a Ferri to realize the a black body. So that is called as the Ferri's construction. So using this Ferri's construction, I am going to explain how this construction will function as a black body. So here is the Ferri's construction of the black body. So a black body is a hollow double-walled sphere with a narrow opening at one end and a projection at the other end. So this is a hollow sphere. This is the hollow sphere with a double wall. You can see here, this is the inner wall and this is the outer wall. And actually in between vacuum is created so that the radiations are not escaping out of this sphere. Vacuum or some other bad conducting materials are inserted. So and the inner wall is coated with this lamp black. The inner wall of this inner sphere is this sphere is coated with the lamp black. Such a construction it is. So it has a one projection at this end and a small opening at this end. This is a small opening. A pinhole is created here to send the radiation. So this is the incoming radiation. So the inner wall is coated with the lamp black so that the radiation entering the container is completely absorbed after repeating reflections on the inner wall. So we can see here a radiation has entered the inner wall of this this hollow sphere, and for example, Rekha is coming like this. It is incident on the this projection first, then reflected in this direction, and it goes in this direction, and here it gets reflected in this direction. Again, it hits the wall and reflected in this direction. So in this way, this ray of light or radiation is taking multiple reflections inside the this container before it get absorbed completely. So that happens. And the atoms of the inner wall of enclosure continuously absorb and re-radiate the photons. And at thermal equilibrium, the number of absorbed photons will be equal to the number of re-radiated ones. So the atoms of the inner wall, that means actually the atoms of this lamp black, because lamp black is coated over the inner wall. So the atoms of this lamp black continuously absorb the photons and also re-radiate the photons. At thermal equilibrium, the number of absorbed photons will be equal to the number of re-radiated ones. So this is about Faraday's construction, and the properties of photons gathered inside the container are same as that of conventional gas. Not all, some of the properties of the photons gathered inside the container are same as that of the conventional gas, and hence it is called as the photon gas. So the properties of photon gas are they do not interact with themselves. So this is also the property of the gas molecules or gas particles. Of course, a small interaction is there due to the presence of van der Waals forces, but the strength of the van der Waals forces is very, very small, negligible. So the same thing is the case here also. The photons also don't, we can say that the photons don't interact with each other. Next, photons interact with the atoms of the wall of the cavity. So then these photons hit the inner wall of the cavity, they interact with the atoms of the inner wall. And photons are indistinguishable, and many photons can have the same energy. Photons are indistinguishable particles, and many photons can have the same energy. Photons have zero spin. And because of all these properties, these photons obey the Bose-Einstein statistics, and hence they are referred as the bosons. And now I am going to derive the Planck's law of radiation based on the statistical mechanics. So the photonic number inside the container do not remain constant and changes with time. So energy can be remain constant inside the container, but the photonic number cannot be constant inside the container because the atoms are the photons are continuously absorbed and re-emitted. Because of that reason, the total photonic number do not remains constant. Hence, for photon gas, we can treat summation of d and I is not equal to 0. For this reason, the constant alpha in Bose-Einstein distribution law is 0. So this is the Bose-Einstein distribution. Here e raised to Ni is equal to Gi divided by e raised to alpha plus Ei by Kt is there. So this constant alpha will have the 0 value, because of this reason that the photonic number is not constant. And thus, you set alpha is equal to 0 here. So this equation becomes Gi divided by E raised to E divided by Kt minus 1. Since the cavity is large compared to the wavelength of the radiation, incident radiation, the energy spectrum of the photon is taken to be the continuous or the continuum. So continuum means all the possible wavelengths will be there. Thus, replacing Gi by G of E and D, this Gi is the number of cells when you are treating a system as a discrete system. But here, since all the wavelengths are possible, the spectrum is a continuous spectrum. So you are changing this discrete quantity with the continuum quantity G of ED and also Ni by N of ED. This Ni is the number of photons inside the container. So the occupation index, which is the ratio of the occupied cells to the total number of available cells, is given by F of E is equal to N of E into D divided by G of E into D. So this is called as the occupation index. So this is the ratio of the number of cells occupied to the total number of cells available inside the container. So this is equal to 1 divided by E raised to E divided by Kt minus 1 as per Bose-Einstein distribution. And here alpha was there, that was set equal to 0 as the total number of photons is not a constant. Then the distribution function is given by from equation 2, you equate these two, N of ED is equal to G of EDE divided by E raised to E divided by Kt minus 1. This equation, this is considered as the distribution function for these photons. Next, let the volume of the black body radiating be V. So this is the volume actually bounded between the two spheres of radii P and P plus dP in the momentum space, as I have shown in the diagram here at the beginning. So here two spheres are there. One is the sphere with the radius P, and another one is the sphere with the radius P plus dP. So between these two spheres, some volume is bounded. That volume is important one. And this P and dP refers to the momentum of the, actually they are the radii of the sphere, but actually they are the momentum of the photons inside the container. And hence these are the coordinates in momentum space. So coming back to the derivation of this Planck's law. So I came here. Then the distribution function is given by N of ED is equal to G of EDA divided by E raised to E by Kt minus 1. So just I am rearranging this equation 2 by equating these two parts. So let the volume of the black body radiating be V. Volume means that volume bounded between the two spheres. The energy of the photons inside the container in the frequency range nu and nu plus d nu is given by E is equal to mc square, or that is equal to h nu. And you take 1c to the RHS, so you will get mc is equal to h nu by c. So this where m is the mass of the particle and c is the velocity. So this is the product gives the momentum, and hence this is p. P is equal to h nu by c. And differentiating this, you will get this as a dp is equal to h by c into d nu. So h by c both are constant, so nu becomes d nu. So it is differentiation of the momentum. Then the volume bounded between the two spheres of radii p and p plus dp. This p plus dp is 4 pi p square into dp. So don't confuse. Actually, here, if you are considering only the coordinate space, these two will be r and r plus dr. But we are considering here the momentum space. That is why in place of position coordinates r, we are substituting p momentum coordinates, and hence it is p and p plus dp is 4 pi p square into dp. This is the volume between the two spheres in momentum space. In momentum space, as you know, different kind of spaces are there: coordinate space, momentum space, and coordinate space plus momentum space gives this phase space like that. Different phases we are considering. Then the smallest volume of the cell is in the phase space, according to uncertainty principle, is h cube. This we have shown while studying the phase space. So the smallest volume of the cell in the phase space, according to uncertainty principle, is h cube. So this h cube, this h cube, this h cube you will get when you will multiply the products of position and momentum in the phase space, because in the phase space there are 3 position coordinates and 3 momentum coordinates. When the position and momentum coordinates of x-axis you are multiplying, you will get 1h as per uncertainty principle. Uncertainty principle tells that the uncertainty in finding the momentum and position and their product is approximately equal to h. There is an uncertainty in finding the momentum as well as position. Both cannot be obtained at a time accurately. So, but the product of uncertainty in momentum and the corresponding uncertainty in the position is nearly equal to h, the Planck's constant, that we have shown separately. Then the number of cells per unit volume of the black body is equal to 4 pi p dp divided by h cube. So this is the volume bounded by the two spheres, that is multiplied by divided by h cube. Then we are getting the number of cells per unit volume in the black body. Then the density of states in the volume V of the black body with the 2 polarization states. 2 polarization states means these photons have 2 polarization state. That means it may have the spin in clockwise direction, or it may have the spin in anti-clockwise direction. So the 2 polarization states are possible. So therefore this becomes G of P is equal to 2 into this 2 comes because of the 2 polarization states, and it is the density of states 4 pi p square dp divided by h cube into V. In terms of frequency, same equation you will write this as 2 into 4,5 h cube. And this P is momentum. As per equation 4, P is equal to h nu by c. And dP is the derivation of that P. So that is h by c into d nu and into V. So this you are substituting from equation 4. Next, so this you have to simplify. You will get this as a 8 G of nu. G of nu is equal to 8 pi V nu square divided by C cube into d nu. Then the energy distribution function as per the Bose-Einstein distribution is f of nu is equal to 1 divided by e raised to h nu by kt minus 1. When you are substituting E is equal to h nu. So this distribution function becomes in terms of frequency or energy. Then the number of photons in the frequency range nu and nu plus d nu is given by like this. It is counted like this. So density of states multiplied by the distribution function gives the number of photons in the frequency range nu and nu plus d nu. So the density of states is given by this much as per our equation 7, and the distribution function as per equation 8 is given by this. So just to substitute equation 7 and 8 here. Next, the energy density, that is energy per unit volume in the frequency range nu and nu plus d nu is given by u of nu d nu is equal to, this is how calculated, energy of each photon multiplied by photon density divided by volume gives the energy density of the photons. So this is equal to energy of each photon, means it is h nu, and photon density as per equation 9 is this much, and divided by volume V is substituted. So now this is h by V, and you substitute the value of what is that, n of nu into d nu as per equation 9. As per equation 9, n of nu d nu is this much. So that you substitute here. So this is n of nu d nu as per equation 9. Then you simplify this one. U of nu d nu is equal to, it is 8 phi h is here, nu into nu square nu cube divided by c cube into 1 divided by e raised to h nu by kt minus 1 into d nu. So actually one v is here, but here also one v is there, that cancelled. So it is not written. So here one v is here, that v is get cancelled. Here is also that is there. This v get cancelled. This is v get cancelled. So it comes out to be 8 phi h 8 phi h nu square is nu cube divided by c cube into this quantity 1 divided by e raised to h nu by kt minus 1. And this represents the Planck's law of radiation, the famous Planck's law of radiation in terms of frequency. So this is the complete derivation of Planck's law of radiation based on statistical mechanics. Thanks for listening.